Afternoon, folks. Going to go ahead and get started here. So appreciate everybody sticking around. Last session of the day. This is an exciting one. I'm really honored to be here and kind of listen to each of these presentations. This afternoon session will be on 4 technologies that could disrupt or have a major impact, so to speak, on the ground heat pump marketplace. So I'm Mitch DeWein. I'm with CHA Consulting, and our speakers this afternoon are Matt Desmarais with Energy Catalyst. Unfortunately, Bob Manning could not be with us, so we will be skipping his slides. Darren Jones with Dandelion Energy, and Geoff Ellison from Envirohire Limited. So with that, I'm going to jump right into things and invite Matt up to start the presentation.
Thanks. Hello, everyone, and thank you very much for the opportunity to speak here today here in New York City. Appreciate it. Thank you to Mitch for our moderator. So today I'm going to be talking about reusing existing hot water infrastructure and doing it efficiently. There's about 2.5 million buildings in New York State that are heated with hot water currently, and it's typically very difficult to retrofit these. So let's jump right in. So there's a traditional thinking out there right now that hot water systems are the worst to retrofit. And it kind of makes sense if you look at it for 3 main reasons. Well, number one, the efficiency of a hot water system is typically quite a bit lower than a comparable ground source a forced air, heat pump. So if you're trying to replicate the high temperatures of a hot water boiler at 180 degrees, frankly, the efficiency is going to be prohibitively inefficient, right? And so the max that you typically want to use is about 120 degrees to remain efficient and have a system that that can get a reasonable COP. But even then, that's a COP of about a 3. Another big problem is that there's this perception that you cannot reuse the existing infrastructure. Now, this is not actually totally true, but there is that perception out there, and that could lead to a lot of major retrofitting and cost. And then you have incomplete coverage. A lot of these buildings would still need a separate chilled air system, for air conditioning and ventilation. So even if you could reuse all the existing infrastructure, you still have other problems to solve when retrofitting these types of buildings. Okay, well, so the one thing that, my slides got a little screwed up here, so sorry, it threw me off here a bit. But traditionally, every plumber in the world would tell you, you can't heat a building with 120 degree hot water. It's just not possible. And this is partially true, but it's also pretty untrue for non-peak days. So the condensing boiler industry, which is a multi-billion-dollar industry, has for 20, 30 years been heating buildings, commercial and residential, with 120 degree hot water. So it definitely does work, and it works fine. But as we all know, systems, a condensing boiler, if it needs to, on a peak day, it can just make higher temperature hot water. So it has that ability to bridge the gap if it has to, right? And heat pumps typically don't have that ability. They can't go up to 180 on the coldest day of the year. And so we need to find a way to bridge that gap. Now, based on our own data logging, what we find is that most buildings can cover about 80% of their peak load with 120 degree hot water. So there's only a 20% heating gap that has to be filled. Okay, so my slide is not working here, but just imagine that moved into place. Going with it though. So here's a partial view of the refrigeration cycle. And I know probably many of you are engineers in the crowd, but I promise there's a point to all of this. So if you look at, this is the refrigeration cycle that would be embedded within a heat pump, okay? So it's all within a box. And then we're making hot water for this external buffer tank, right? So let's say we're making high temperature hot water, 120 degree, 115, 120 degree hot water. So we have this refrigerant vapor coming out of the compressor, It's a superheated vapor. It's going to condense into a liquid at the heat exchanger. Now, that's a good thing. That's what it's supposed to be able to do, right? And as it does that, we're getting that phase change energy is being passed to the water, and it's making hot water for the hot water tank. Perfect. But then downstream of that, if you follow it, it goes to the expansion valve, right? And if you left it that way, what you would see is that the expansion valve's job is to basically absorb heat. On the other side of that expansion valve, it's kind of like a freezer. It's there to cool things down. And so if you inject 120-degree liquid refrigerant into something that's trying to cool, they are going to fight against each other. That is actually the exact reason why, as you go to higher and higher temperatures, as you make higher and higher temperatures with a refrigeration system, the efficiency continuously drops, right? That's just the laws of physics. And it's for this very reason, because the more that refrigerant gets hotter and hotter, the more that it's going to be fighting against itself on the back end, on the evaporator side. So this is the point where this little air coil is supposed to pop up in my PowerPoint, but that's already there, as you can see. So our solution at Energy Catalyst, and let me just press this to see if it does anything. Nope, okay. Well, so our solution at Energy Catalyst is to reduce that temperature using an air coil. So we can reabsorb some of that waste energy by using the relatively cool air temperature that we're trying to heat in the first place. So we can take 70-degree air, pass it through an air coil, and use that as a subcooler. Now we're delivering 70-degree refrigerant into that expansion valve instead of 120-degree. We're also releasing heat directly into the building. We're making hot air and hot water at the same time. This is what we call the double hybrid refrigeration cycle. And so one of the things that this leads to is that now if we build a heat pump like this, you have to put that air in close proximity to where it's going to be used. You have to put your heat pumps in relative proximity to where the spaces that you're trying to heat up, right? It's like you want to spread them all throughout a building, right? But if you do that, you can check all three major boxes. Efficiency increases dramatically because of the energy recovery. We typically see, it depends on, of course, what temperature you're running at, but COP of 4.5 to 5 is 100% achievable. We can reuse all of the existing infrastructure. Remember, we get 80% of our heat out of the baseboards and radiators that are already in place, and we can fill the hole, that 20% gap, with the forced air. And then we can get air conditioning. We can put some ductwork into the building, not replacing all of it with forced air, but we can use just a little bit of ductwork, about a quarter as much as you would typically use, about 100 CFM per ton, and we can use that to fill, to provide supplemental heat. So I know a lot of you are engineers and want to see an example. So let's jump right into one. This is Hawthorne Valley School. It's in central New York. There's 4 buildings. We're doing the entire campus this upcoming summer, 60,000 square feet in total. The building has all hot water baseboard throughout the whole campus, all right? So, okay, my slides didn't quite work out here. So this is the building. You can kind of see it with the ductwork, and it's a little small, but there are 2 heat pumps on the bottom floor here. And then on the next slide, you can see there's 3 heat pumps here. So we're putting the heat pumps throughout the building in close proximity. There's relatively, it kind of looks like a lot here, but the ductwork itself is very, very small, about 100 CFM per ton. And the benefits of doing it this way is that we can provide chilled air, supplemental hot water, ventilation, and air filtration, all with that very, very limited duct system. And it's all done with about a quarter the size of a normal forced air system. We haven't made any other changes. We're using all the existing hot water infrastructure. Now, this is very important to have a small amount of retrofitting because it's a school. And we need to go and do all this work over the course of a summertime. We only have 2.5, 3 months to do it all. So doing that in a very short time frame is extremely important. The school itself, a very high priority for them was to reduce the risk of asthma symptoms and to be prepared for the next COVID incident, so that is now provided. Now, for the engineers and the crew in the crowd here who might be looking at this and thinking about what would that look like over the course of the season, let's go through on a season-by-season basis. So right now, it's October, so kind of a transient load kind of period. And so you might have some zones that are in cooling and some that are simultaneous heating. In that case, the equipment can produce simultaneous chilled air and hot water, which can be used in other zones. It could be stored. During the peak heating season, we would cover the load by 80% hot water, 20% supplemental hot air. And then during the peak cooling season, somebody's about to raise their hand, hopefully, and say, well, hang on, we're not going to be able to get the full capacity if we only put such a small ductwork in. We're not going to be able to do full cooling. That's probably true. But also, this is upstate New York. This is a school. And some amount of cooling is a lot better than no cooling. And so even though you can't necessarily cool down the rooms, to 65 degrees, you might be able to definitely take it from 90 degrees down to 80 or 70, 77, something like that. So you're still getting most of the benefits. Here's my favorite slide, and it is basically my last slide here. The overall expected efficiency is a 5.1. 5.1 for a building with existing hot water. That's unheard of. That's exceptionally high. And at a project cost of $25 per square feet, which is also very, very cost competitive. That number, by the way, is before the 40% rebate, before any NYSERDA incentives, before any of the utility rebates. This is actually one of the, this is a very, very, if they had just gone and replaced their boilers instead, it almost would have been the same cost. So just one more time, our patented technology, we call it the double hybrid. We manufacture this equipment in Troy, New York. And for the 3 reasons there that we can solve the efficiency, reusing the existing infrastructure, and do it all with very, very limited ductwork, that's what we believe makes us a good candidate for cutting-edge technology. Thank you very much. Scroll through these for you.
Thank you, sir.
Yep.
Next up, Darren.
Thank you, Matt. Seen bigger crowds at Trump rallies, but thank you guys for sticking around here till the end and listening to us speak. I really appreciate the time. So I've been with the company, Dandelion, for a long time, since the very beginning almost, about 6.5 years. I've worked in a number of roles within the organization. We originally set out to be a residential retrofit geothermal heat pump installer. We wanted to help the millions of homes that exist out there today move to a more sustainable way of heating and cooling. And so we ended up developing a heat pump all of our own. Over the last 7 years, we've installed almost or a little over 3,000 heat pumps, primarily in 3 states, New York, Connecticut, and Massachusetts. These retrofits gave us insight into some of the biggest friction points for homeowners who want to adopt geothermal. So this is reflective of installations in Ellison territory because it was the data that I had kind of on hand when I was asked to make this presentation, but it's pretty representative of the Northeast market that we serve. So the key takeaway here is really that only 7.5% of the projects that we install just need a heat pump. So 7.5%, cut the old one out, slide the new one in, and walk away. But most everybody else needs some kind of infrastructural improvement to actually make the heat pump work as it should, or at the rated efficiencies that we're sort of desiring. So we set out to sort of address these challenges by making our own heat pump. Our goal was really just to make a heat pump that is likely to solve some of those infrastructural needs through the equipment itself, reducing ductwork modifications or main electric panel upgrades, anything that we can do to sort of solve some of those problems by just making a better heat pump. This unit was just optimized for heating, so we just wanted to make a heating-forward heat pump and think about it from that perspective because most of our, well, all of our clients are here in this cold climate. And so the more BTUs that you can get, the more square footage that you can serve. So, you know, there's a pretty table up there. We got some heat outputs that are a little bit higher than some of the units that we saw in the marketplace, and that's great, right? More capacity is always good. We designed it to be easy to install. One electrical connection is all that's required for this. Essentially, we managed to pack a 10 kW heat strip in there, broke it up into sections. 1/3 of that is able to operate with the compressor, so it acts as a boost or supplementary heat on those cold, cold nights that we need just a little more BTUs than we can get. I think February 4th, 4 a.m. And then the compressor, once locked out, has access to the remaining heat strip capacity. So in a true emergency situation, you still got your 30+ thousand BTUs of heat so that you're not freezing to death while you wait for a service guy to come out and take care of you. One of the other challenges was ductwork, retrofit ductwork, right? These are houses that were never thought about with a heat pump in mind, right? We were never thinking about providing that size of ductwork so that we could, be warm and comfortable in our houses. And we wanted to basically make something that behaved a little bit more like a furnace and can operate at lower airflows. So we're able to push out 100% of the heat that we need as low as 230 CFM per ton. When you set the airflow for heating and cooling on the control board, in the event that second stage cooling needs to be locked out, it just automatically does so. And that's really how we're able to push more heat on the heating side. So one of the other labor-intensive parts of installing a heat pump is getting the pumps together and getting everything integrated and setting the flow. So we just built them in. We got variable speed ground faucet pumps included in there, and then they automatically adjust the flow rate. So it saves guys a little bit of time. So I don't know what's next. Maybe some of you guys out in the field there got some ideas. Obviously, we got some very intelligent people, myself not included, up here talking about the transformative things that we're trying to do in the industry. And we're excited about it. So we just decided to tackle the biggest problem that we solve and saw, and pretty happy with the success of the product that we've made, and hope to install them in as many homes as we can and help some of those people that kind of otherwise have been able to say yes to geothermal to be able to do so. So that's it.
Thank you, sir. And up next, last but not least, Geoff will be coming to present some insights from the UK market.
Thank you. Let me put that there so I remember who I am. So what's the lasers?
Just left and right.
Okay. So I'm going to deal with today UK legislation, some of the standards we work to, and also the testing of loops. Now, you don't know me. I'm from the UK. You don't know my company. So for background, I used to be originally a government research scientist. I have been a technical director of a national waste management company. And my current companies are a plant hire business, a renewable energy company, and also a drilling business. I sit on two trade associations. The first one is the British Drilling Association, where I sit on their Technical and Standards Committee. I also sit on the Ground Source Heat Pump Association's committees for standards and also what we call the Drillers Action Group. Now, our Environment Agency now considers that heat is a pollutant. That was a bit of a shock to me when it came out, maybe a bit of a shock to you. And the way they notified us was they released what we call a statutory instrument. It was number 651, and it said that if you need to put in a heat loop, then you have to have an environmental permit. Now, environmental permits are usually for things which are highly polluting, sewage works, incinerators, waste sites, cement works. And it was a bit of an over-the-top view, in my view, to actually include those into the ground source sector, because effectively you require an environmental permit for every loop that you put in. But as I read through Statute Instrument 651, there came a paragraph there which was of great comfort to me, which said that you could have an exemption from having a permit if you worked to certain name standards. So I then scrabbled through the appendix there to see what these escape clauses actually meant. Now, 3 of those standards were written by the Ground Source Heat Pump Association. That's their vertical borehole standard, the shallow ground source standard for horizontal systems, and also the thermal pile standard, which is used in construction. Now, those standards apply to the entire project, the design, the materials you use, any components, how you install them, and also how you test the system. And I'm going to be dealing now with how we actually test the loops. Now, polyethylene pipe is a substance which suffers from viscoelastic stress. We also call that creep. So it expands under pressure, and when it does that, that affects the readings that you take. So the GSHPA have borrowed a standard from, it's a British and European standard, it's BS-EN 805, it's been around since 2000, and that's a test for installing water pipes. Okay, that's also subject to viscoelastic stress, and so that's been around for 24 years, and it takes into consideration the fact that when you increase the pressure, the pipe expands. The pressure drop test in BS-EN 805, and by the way, that's another one of the standards which is mentioned in our statutory instrument as one to work to avoid the permit. First of all, you raise the pressure to the test pressure, then you have a controlled rapid reduction in pressure of 10%, and then you test the pressure of the pipe as the pipe actually contracts. Wasn't quite expecting that. I was expecting to see a graph on there.
you try going one more forward?
Try one more forward, it's not that, so there should be a...
All right, I can quickly download something.
Any?
Let's see. I'm gonna have plenty of time. We're using Dropbox. PowerPoint doesn't work as well. Yeah, there's like two. There's two slides.
The slides in the graph.
You mean when I left? Maybe this will work.
Should. I get to do mine again, right?
Way forward. Keep going. Which slide?
Keep going. Keep going. That's the one.
Is that what you're looking for?
That's the one I was looking for.
There we go. Thank you.
You can appreciate describing that would have been a little tricky. Right, that's what the pressure drop test looks like in British standard and European standard 805-2000. What you do initially is you have a pressurization phase. This goes up to 12 bar. I'll translate that into American, which is 176 psi. Doesn't have to be 12 bar, that's set by the designer, but that's the sort of pressure we're talking about. So you raise the pressure to the test pressure. At that point, you see that the pipe will expand, that reduces the pressure, so your pump carries on for a 10-minute period and maintain that pressure at 12 bar. You then stop the pumping and isolate the loop itself. What you have then is the pressure will drop naturally for a 60-minute period. If it drops by more than 30%, the test has failed. The pipe's got a hole in it. And then you have a rapid reduction phase, which is 10% of the original test pressure. I'm saying 12 bar, 1.2 bar. You'll be saying 176 psi, 17.6 psi. You then monitor the pressure for 30 minutes. The pipe rebounds, and then you take a pressure reading every 10 minutes. And if the pressure between those two phases doesn't drop by more than 0.1 of a bar, or 1.5 psi, then that pipe work is sound. And that pressure test has been around used in Europe for the last 24 years. So that's a test which takes place in less than 2 hours. So the GSHPA standards, all of the standards work in accordance with BS-EN 805. They also have specific requirements in the GSHPS standard. The first one is that you use effective drinking water. The second one is you remove all the air. Air will affect the results. And also you test the flow in that loop in 2 directions without disconnecting the pipework. So, the loop test apparatus. What I've been working on is an automated system which works to that standard. So the features of it are, well, we say we use potable water. If water's available on site, use it directly. If the water's been standing around for a while, it may have some contamination. For the first thing we do is we filter that water and we hit it with UV light to sterilize it. We remove the air by having a twin degassing tank to remove that. The unit will then do the pressure drop test in accordance with BSE and 805. It will then test the flow in both directions without disconnecting. All the results that we take are electronic. They're recorded and stored for export. We also record the position of the loop by GPS. And finally, we make a camera impression of the loop itself, where it's positioned, and also inside the unit for troubleshooting purposes. So our pilot unit actually looks like this. It's inside a towable container because this is to be used at the point of commissioning. Well, before you commission, at the point of installation, before you commission it, you will test it to make sure it's actually worth commissioning. On the left side of this container there, you can see the 2 degassing tanks, a motive pump. We have a pressure release valve there, which means if someone's misprogrammed the system and we're in danger of bursting the pipe, that's going to blow first. If we go to the other side of the container, we have the treatment system there, and then an arrangement of valves which will divert the flow through the first sequence and then the second sequence. In close-up, there's a filtration system there which will take it down to about 5 microns, and then we have a UV sterilizer which will zap the bacteria so no bacteria are introduced into the loop itself. On the other side of that, we have the feed from the pump, which will come in, go down into the loop, return back from the loop, and return back to the degassing tanks. And then those 4 valves will alternate, and we'll have the flow coming in this way. It will divert through that way, go out through the reverse flow, come back, and then go back to the degassing tank itself. So that tests the flow rate in the 2 directions which we require. So what are the system benefits? Well, first of all, it's fully automated. All the person who's using the equipment has to do is connect the loops, fill the tanks with water, set the pressure, and press the start button. If you can cook a microwave meal, you can use this system, okay? Robust. Now, I employ drillers. I know what they're like, and they can break just about everything. My drillers have all used this. First of all, they like it because it's simple. And secondly, none of them have managed to do any damage to it whatsoever. It doesn't interrupt drilling operations. So you set this thing going, leave it to work, you can carry on drilling, which means you'll be generating cash from your drilling operations while this thing goes through its process. You don't sit there and watch your dishwasher as it goes through its operation, okay? You leave it to run. The apparatus has been calibrated. It's accurate, it's consistent, and it's repeatable. All the data that you generate is stored electronically. Nobody can manipulate that. There could be no cheating. Okay, I'm not saying that people are going to cheat, but it would be very tempting sometimes if someone's marking their own homework to say it worked when maybe it didn't. The GPS means that you are testing the loop in the place where it actually is, and also the verification of the position of the loop by camera means that you're not testing a piece of pipework, you are actually testing the loop you've installed. You cannot use the system unless you gain access through a fingerprint identification. You don't get that until we've trained you. All these items mean that the loop will then qualify for warranties and guarantees, which actually means something. So, what are my objectives? First thing is to raise the quality of the ground source heat pump installation to cover the entire project. We want to maintain and increase confidence in the sector by having and working to a published standard. We want to generate and maintain an accurate and reliable database for loop installations. Loops will be operational for 50, 100, 200 years. We saw sites on Monday where you're building on top of those loops. Those buildings are permanent. You're going to expect your loops to work for hundreds of years. It's worthwhile putting the effort in at the point of installation to see if they work properly. Fourthly, it confirms to my Environment Agency that the system is integral, it's worked in accordance with the standard, and that way it stops me having to go and get them a permit. And lastly, we're working on continuing development work on this process. The next thing we're looking at is actually confirming the depth of the loop in the ground, and also its verticality. When we drill, it doesn't go straight down. We know that. We get deviation on there. This unit will be able to monitor the position of the base of the loop to the top in 3 dimensions, which also means we can have the bore field, maybe 30, 40, 50 boreholes in there, all in a matrix there, which we can actually demonstrate back to the designer with regard to spatial separation, and also to confirm that we haven't damaged borehole 3 when we actually installed borehole 6. But that's work we're on with, and that's coming on quite nicely. So that's the end of my presentation. So thanks for staying behind, and quite happy to answer any questions you may have.
Second chance at this?
Do you want to go back and bring up your slide?
I was joking.
Are you sure?
All right, then do your questions. Why don't you ask a few, and then if he decides to change his mind.
Good. Put it up to show the graphic. Anybody have questions? You need to bring a mic.
Yeah, I thought you were going to do the questions. This is you, right, Matt?
Yeah, it's that one. That was the image.
For the Dandelion heat pump, is it commercially available, and can you buy it without having Dandelion install the borehole?
Yeah, it's available nationally. And if you're a ground source heat pump installer, you should be able to buy one. In case you all didn't hear me, yes, it's available nationally. If any ground source heat pump installers are interested in purchasing them, they're available for sale. No, we don't have to drill the loop, although we'd love to.
I don't get paid enough to do this.
Back there.
Thanks for the presentations, everybody. Darren, I'm curious, what's the largest application that you've seen? Have you gotten into the commercial spaces or light, maybe multifamily residential, or is it really like targeted on those single family homes?
Yeah, the tonnages are 3 through 6, so they're really designed to be retrofit, but they could work in commercial applications that are suitable to those tonnages. It's just a package unit, a forced air package unit.
Thank you.
Any other questions? Questions?
Geoff, what's your business model, my brother? So you have this really cool thing. Can I buy one?
I only have one at the moment. That's my prototype.
I saw it, yeah.
When it's ready, you can buy it. The business model is that we're looking to hire these units. Certainly in the UK, there's a market there because we now have to comply with our permitting regulations. And so we're building a hire fleet when this one's completely finished, and that will be available. And we were rather hoping that some people in the United States might see there's a potential here, and they may think there may be some scope there for moving into this side of the pond.
Any other questions? Okay, great.
All right, let's keep this going. This is not really a question. This is more like an opportunity to bring out an idea, and this is all about new ideas, so I thought this might be appropriate. But I know somebody who is willing to put together some software that will transverse the NYSERDA roadblocks to applying for all of your benefits when you need to keep track of your apprenticeship hours, your rebates, your refunds. And a lot of people are complaining that they are really sick of just spending so much time on book work. This would be like an app that's one-stop shopping. You push a button, done, one and done. So if there's any interest in that, I just thought I'd throw that out there because I don't know, I'm trying to think how to streamline things. Some of these great technologies that were discussed seem to be streamlining and overcoming problems that exist in the current marketplace, and that might be another tool for contractors that would be helpful. So I just wanted to bring that up. Sorry, it's not a question.
So Matt, because I needed to leave for a couple of minutes and I missed your presentation, I'm going to ask a question. You asked a question and did. So, the question that I have for you is, did you talk to the audience about the factory and or your expansion and how you're going to deal with the thousands and thousands of heat pumps we need to get across the country?
Yeah, I made a brief mention of it. Obviously, this is a panel more focused on the technology, so that was my focus. But for those who don't know, Energy Catalyst has won some Department of Energy money as well as some funding from NYSERDA, as well as the Empire State. Thank you all to those organizations if you're in the room. But due to those, in part to those grants, we're also in part to just our overall growth in the industry. We have built a 22,000 square foot facility in Troy, New York, and are taking manufacturing pretty seriously up there. We are manufacturing the units that you just saw. The actual ones are blue, so sorry about the old image on our slides. But and then we're also building twister ground loops up there. So we're trying to enhance and build more New York-based heat pumps. So to the extent possible that we can, provide for the market, we're very glad to do it. So. Thank you for finally putting my slide up in the way that it was meant to go. I actually had a question for Geoff. So you when you do that test, you bring it up to 12 bar, 170 PSI. What happens if the pipe blows? Like because it's already set in the hole, right?
Well, if it blows at that, then the pipe wasn't very good in the first place, because the pipe's rated 18 bar. Well, ours is anyway.
Gotcha. Okay.
So we have our pressure release valve in there, because if somebody did intend to operate the thing at 5 bar and press the 5 twice and was aiming for 55 bar, then the pressure release valve would go before the pipe would wet.
Is this, sorry, one clarification, and you might have said it, but I just might have missed it. Are you hydrostatically pressure testing, or are you using compressed air at this point?
We're hydrostatic testing. In the UK, it's illegal to use compressed air. We have a health and safety guidance document, GS4, which prohibits you using air.
Okay. Interesting. Yes. Thank you.
So Matt, I have a question for you.
Sure.
So we heard from the footprint general geography that's being targeted by the Dandelion team and where they've kind of located their systems. As you were developing your technology, did you think of a specific climate region or climate zones, or are there any restrictions around where you think these pieces of equipment would be useful?
Yeah, thank you. So when we started out about over 5 years ago now, the original goal was to produce a unit that was great for the Northeast, where there's a lot of hot water, buildings with existing hot water heating systems. So definitely that's our primary market, and it probably will continue to be the greater New England, Northeast area will be a major market for us. But we are already shifting and seeing the writing on the wall. So we have a forced air model, for instance, that can do all domestic hot water directly. It's great for new construction. It's great for any southern climates or other areas that have existing forced air systems. So we're building in new technologies that'll be, better suited and applicable for markets that aren't just all hot water.
Great, thanks.
Good question.
Anyone else with other questions? We have one. If you don't mind, could you let us know who you are when you ask?
I was going to, Billy Roberti, Green Choices Consulting. Matt, can you use your system to generate domestic hot water?
Yeah, so our hot water models, which has the hot water actually going through radiators and baseboards, et cetera, you wouldn't want to drink that water. So we have an indirect hot heat exchanger that goes in there, but we do recommend that be a preheat for the domestic hot water. Not to say that it couldn't be used as a dedicated hot water heating device, but if you did that, then you wouldn't be able to set your hot water temperatures back in the shoulder seasons. It's much better to be able to reset your hot water temperatures back to 100 degrees on a mild day and get the better efficiency on the compressor, and then just use, an air source hot water heater or something like that, or even just straight electric for that remaining, couple of degrees. On our forced air only models that are not going to interact with any hot water heating systems, those ones can do domestic potable water. They have a different heat exchanger in them.
Alrighty, well, thank you to our presenters. Another round of applause.